The Sun, our life-giving star, is around 4.6 billion years old. It formed from a massive cloud of gas and dust called the solar nebula. The Sun is enormous, making up 99.8% of the total mass in our solar system. Its powerful energy is created by nuclear fusion, a process where hydrogen atoms combine to form helium, releasing an incredible amount of energy. The Sun might seem like a glowing ball of fire, but it's much more complex and fascinating than that. To understand how the Sun works, first we need to explore its layers. Each layer plays a unique role in creating the heat and light that reach Earth. At the center of the Sun lies its core, where the magic of nuclear fusion happens. Temperatures here soar to about 15 million degrees Celsius. This is where hydrogen is transformed into helium, releasing the energy that eventually reaches Earth. The core is the Sun's energy factory and is the key to its brilliance. Above the core is the radiative zone. Here, energy from the core travels outward as radiation. This energy takes a staggering 100,000 years to move through this layer because it bounces around so much, like a pinball in a never-ending game. The radiative zone is incredibly dense, and photons of light slowly inch their way through. The convective zone is like a boiling pot of water. Hot plasma rises, cools off as it nears the surface, and sinks back down to be reheated. This process creates convection currents that help move energy closer to the Sun's surface. These bubbling motions often appear as granules when viewed through a telescope. The photosphere is what we see when we look at the Sun. It's the Sun's outer shell and is where sunlight is emitted. The temperature here is cooler compared to the core, around 5,500 degrees Celsius. Although it's not solid, the photosphere appears smooth and bright, like a glowing disk. Next, the chromosphere is a thin layer above the photosphere and is often called the Sun's lower atmosphere. During a solar eclipse, it can appear as a reddish glow around the Sun. This layer is packed with activity, including the rise of solar flares. The corona is the Sun's outermost layer, stretching millions of kilometers into space. It's incredibly hot, even hotter than the layers below it, with temperatures reaching 1 million degrees Celsius. The corona is visible during a total solar eclipse, appearing as a glowing white crown. Scientists are still studying why it's so much hotter than the Sun's surface. The Sun is primarily made of hydrogen, about 74%, and helium, about 24%, with tiny amounts of other elements like oxygen, carbon, and iron. These elements fuel the Sun's energy production, making it the powerhouse of our solar system. The Sun isn't always the same. It follows an 11-year cycle of activity. This cycle is marked by changes in the Sun's magnetic field, which flips every 11 years. During the solar maximum, the Sun is highly active, with more sunspots, solar flares, and coronal mass ejections. In contrast, the solar minimum is a quieter phase with fewer sunspots and less activity. Sunspots are dark spots that appear on the Sun's surface. They might look small, but don't be fooled. They can be as large as Earth. Sunspots are cooler areas caused by disturbances in the Sun's magnetic field. These spots are more common during the solar maximum and serve as indicators of the Sun's activity level. The number and size of sunspots help scientists track the solar cycle. The Sun doesn't always stick to its usual rhythm. Historical records show periods of unusual solar activity. For example, the Maunder minimum occurred between 1645 and 1715 when very few sunspots were observed. This period coincided with the Little Ice Age, a time of cooler global temperatures. Understanding these fluctuations is essential because they have significant effects on Earth's climate and technology. Solar flares are among the most awe-inspiring events in our solar system. Just imagine a sudden, powerful burst of energy erupting from the surface of the Sun, releasing intense heat, light, and radiation into space. This is a solar flare in action. These eruptions occur when the Sun's magnetic energy, stored near its surface, becomes unstable and suddenly releases enormous energy. It's like the Sun letting off a fiery sneeze, but on a cosmic scale. The energy released by solar flares is astonishing. These bursts can produce light so bright that they momentarily outshine the rest of the Sun. They also emit harmful radiation, including X-rays and ultraviolet light, which travels at the speed of light and reaches Earth in about 8 minutes. Solar flares often occur in regions near sunspots, where the Sun's magnetic fields are particularly strong and tangled. Scientists classify solar flares into 5 categories based on their intensity. A, B, C, M, and X. Think of these like earthquake magnitudes, but for solar eruptions. A-class flares are the weakest and barely noticeable, while X-class flares are the giants, capable of disrupting satellites and even electricity grids on Earth. For example, an X-class flare in 2003 disrupted satellite communications and power grids in some parts of the world, reminding us how powerful these solar events can be. When a solar flare occurs, its effects ripple through space. For Earth, the radiation from a solar flare can disrupt communication systems, particularly those relying on satellites. Just think GPS signals failing mid-flight or radio communications cutting out on a ship in the middle of the ocean. Solar flares also pose a threat to astronauts in space, as they're exposed to high levels of radiation that Earth's atmosphere usually blocks. Without proper protection, these radiation doses could damage both health and equipment. However, solar flares are not all bad news. They're responsible for creating breathtaking auroras near the poles. These dazzling light shows occur when charged particles from the flare interact with Earth's magnetic field, creating glowing curtains of green, red, and purple in the night sky. While they highlight the sun's immense power, these events also remind us of the delicate balance between beauty and danger in our universe. If solar flares are sudden bursts of energy, coronal mass ejections, CMEs, are their larger, more powerful cousins. A CME occurs when the sun releases an enormous bubble of plasma and magnetic fields from its outer atmosphere, known as the corona. These massive blasts are so powerful that they can send billions of tons of charged particles hurtling through the space at astonishing speeds. CMEs are typically associated with periods of intense solar activity, known as the solar maximum, when the sun's magnetic field becomes especially tangled and unstable. You can take it as a tightly wound rubber band suddenly snapping. This is similar to how CMEs form. When the sun's magnetic field lines twist and break, they release a colossal cloud of plasma and energy, stretching millions of kilometers across space. These events are truly cosmic in scale. Unlike solar flares, which release energy almost instantly, CMEs unfold over a longer period and on a much larger scale. They can take 1 to 3 days to reach Earth, depending on their speed. CMEs also have a broader impact, affecting not just satellites and communications, but also the entire magnetic environment around the Earth, known as the magnetosphere. When a CME collides with our planet's magnetic field, it can trigger a geomagnetic storm. The effects of a geomagnetic storm can be both stunning and alarming. On the positive side, CMEs can produce some of the most vivid auroras ever seen. These light shows are visible much farther from the poles than usual, sometimes lighting up skies over cities like New York or London. However, the same geomagnetic storm that creates these auroras can also wreak havoc on technology. For instance, a powerful CME in 1989 knocked out power grids in Quebec, Canada, leaving millions without electricity for hours. The impact of CMEs extend beyond light shows and power outages. They pose significant risk to satellites in orbit, potentially damaging their electronics and disrupting communication networks. GPS systems, which we rely on for navigation, are particularly vulnerable to the charged particles from CMEs. Additionally, airlines that fly polar routes can experience communication blackouts, forcing them to reroute flights, which cost time and money. The economic implications of severe CMEs are enormous. Power grid failures, communication disruptions, and satellite damage can lead to billions of dollars in losses. Governments and space agencies around the world are working to improve their ability to predict CMEs and minimize their impact. One of the most mesmerizing effects of solar activity is the aurora, often called the Northern Lights Aurora Borealis in the Northern Hemisphere and the Southern Lights Aurora Australis in the Southern Hemisphere. These dazzling light displays occur when charged particles from the solar wind interact with Earth's magnetosphere, the protective magnetic field that surrounds our planet. The particles from the sun collide with gases like oxygen and nitrogen in the Earth's atmosphere, causing them to glow in brilliant shades of green, red, and purple. The intensity of these auroras depends on the strength of the solar activity. During strong geomagnetic storms, auroras can be seen far from the poles, lighting up skies over regions that rarely experience such phenomena. People lucky enough to witness an aurora describe it as magical, as if the sky itself has come alive with color and motion. The same solar particles that create auroras can wreak havoc on modern technology. When a strong solar storm hits Earth, it can disrupt satellites orbiting the planet. These disruptions can lead to failures in GPS systems, communication networks, and even weather prediction systems. It's like driving and suddenly losing GPS signals or having a flight delayed because air traffic control systems are temporarily shut down. Such events have happened before and could happen again. Power grids on the ground are also at risk. High-frequency radio communications, often used by ships, planes, and emergency responders, can also be disrupted by solar activity. The higher levels of radiation during a solar storm can interfere with these signals, making communication difficult at critical times. Solar activity doesn't just affect technology. It can also pose risks to living beings, especially those outside Earth's protective atmosphere. Astronauts in space are particularly vulnerable. When a solar flare or CME occurs, it releases high-energy particles that can damage the human body. Without the shielding of Earth's atmosphere, astronauts risk exposure to harmful radiation, which can lead to long-term health problems. Even on Earth, people flying at high altitudes, particularly near the poles, may be exposed to slightly higher levels of radiation during a strong solar storm. Airlines often reroute flights to avoid these areas during intense solar activity, ensuring passenger safety. Several space missions and observatories are dedicated to studying the sun. The Solar and Heliospheric Observatory has been observing the sun since 1995, providing valuable data about its activity. It monitors everything from sunspots to CMEs, helping scientists understand and predict solar storms. The Parker Solar Probe, launched in 2018, is one of the most ambitious solar missions ever. It's flying closer to the sun than any spacecraft before, diving into its corona to study the mechanisms behind solar wind and magnetic activity. The probe's findings are helping us understand the sun's behavior on a deeper level. Another critical tool is the Solar Dynamics Observatory, which captures high-resolution images of the sun in various wavelengths. These images reveal details about solar flares, sunspots, and other phenomena, allowing scientists to track the sun's activity in real time. Modern technology has made it possible to monitor the sun like never before. Satellites, equipped with advanced instruments, can detect changes in the sun's magnetic field and measure solar wind speed. Data from these satellites is processed in real time, allowing scientists to issue warnings about incoming solar storms. This ability to predict solar activity has significant benefits. When a CME or strong solar flare is detected, power companies can take steps to protect their grids, and satellite operators can adjust their systems to minimize damage. Airlines can reroute flights, and astronauts can take shelter in shielded areas of their spacecraft. Predicting solar storms isn't just about avoiding inconveniences like GPS disruptions. It's about safeguarding the critical systems that our modern world depends on. From communication networks to power grids, the potential for damage from a severe solar storm is enormous. By understanding the sun's behavior and preparing for its outbursts, we can reduce risks and ensure that life on Earth continues smoothly. While the sun feels eternal, it is, like everything else, subject to time. The sun is currently in the middle of its life, about 4.6 billion years old. It's expected to continue shining for another 5 billion years, but its activity and appearance will change significantly over time. As the sun ages, it will gradually become hotter and brighter. Over the next billion years, this increase in brightness will make Earth less hospitable, as higher temperatures will cause oceans to evaporate and life to struggle. This slow transformation is a reminder of the delicate balance that allows life to thrive on our planet. Eventually, the sun will run out of hydrogen in its core, the fuel that powers nuclear fusion. When this happens, the core will contract, and the outer layers will expand. The sun will grow into a red giant, swallowing the inner planets, including Mercury and Venus, and possibly Earth. During this phase, the sun will shine with a reddish hue, much larger and cooler than it is today. After its red giant phase, the sun will shed its outer layers, creating a stunning cloud of gas called a planetary nebula. What remains will be the core, which will sink into a white dwarf. This small, dense remnant will no longer produce energy, but will grow faintly as it slowly cools over billions of years. Ultimately, it'll become a cold, dark object, marking the end of its life. What do you think? Is it really going to happen that the sun will go cold, or another star will take its place? Share your thoughts in the comments below. And if you want to know more about space, don't forget to watch our video on how difficult it actually is to travel to Mars.